Hmm. Hi, everyone. My name is Peter Boza. I work at Vision Analytical, and I'm also here with Sanjeet Roy from OFI Testing. That's been great at helping out with some of the data. And what we're going to be discussing today are some data from a new, relatively new technique that is in this industry, which is dynamic image analysis, and really show what the benefits are to the drilling engineering community, uh, give you more information at the well site. So, talking a little bit more about particle size, there's a lot of applications with particle size, but if you look at the areas of the methods, there's an enormous amount of methods. So this just shows a few of them, but uh, definitely in a specific size range, you'll see there's a way big overlap. And the different applications depends on the different methods depend on the application. But the ones we're going to be talking about today are static light scattering, or also known laser diffraction. And we're going to be talking about this new technique, which is it's automated microscopy. It's an automated microscope, basically. So, laser diffraction is, I think everyone is pretty much familiar with what that does. I think many people here are using laser diffraction. It seems to be the most common method. It's an excellent method. It's been around for a long time. And the way laser diffraction works is it actually takes oh, it actually takes the a laser and it shines it onto a particle, and the particle light is diffracted, or from the particle. There's a lot of other intricacies involved if the particles are smaller and translucent, but for the most part, laser diffraction basically it's just measuring the angular data of diffracted light from a particle. Okay, um, this is a an indirect measurement technique. You're not necessarily measuring the size of the particle; you're measuring the angle of data, the angle of diffraction. Mathematics are put in, and then you come up with a particle size. All the particle size rendered from laser diffraction will assume the particle is round. That's the case for all types of indirect measurement techniques. Dynamic imaging is again, relatively new technique. It's been around maybe actually for several years with microscopes, but dynamic imaging has been around maybe about 20 years, and mainly is come about with the advent of faster computers. It's a direct measurement technique. So, a direct measurement technique will measure the actual particle itself. So, basically, you have a light source and you're taking images of these particles. Yes, there is a measure that will give you particles as if they were round, but there's also ability to give you shape measures, how round they are, how uh, smooth they are, how dark they are, the length, the width. So it gives you different techniques. So these are the two techniques we're going to be talking about. So why would it be different in this application? Well, mainly because not all particles are round. Again, so looking at indirect measurement techniques that we just mentioned, again, we're not necessarily measuring the size of the particle. We're actually measuring the diffracted light from the particle. As a result, the data will give you a equivalent spherical diameter. So, in the case of this particle, which we zoomed up here, if we assume this particle is round, it will be represented as about a 100 micron particle. You can have an air bubble that's about a 100 micron particle. You can have a fiber that could be represented as a 100 micron particle. So, indirect measurement techniques will always assume all particles are round, whereas direct measurement techniques will take the actual size of the particle, image of the particle, and it will actually give you all the different 32 different shape measurements. It'll give you size. Again, it'll tell you it's a 100 micron particle, but it would also give you a very varied amount of different shape measures, such as circularity, smoothness, aspect ratio, opacity. So you get much more information. And again, this is very practical when your particles are not all necessarily round. So to go over briefly, as brief as I can, how dynamic imaging works. Again, particles are in motion, and it uses a high-speed camera. Um, there is the ability of the software converting everything over to a binary image. And then once it converts it to a binary image, there are 32 different shape measurements taken for every particle. It's all added to the statistical histograms, and then we save every dynamic imaging saves a thumbnail of every particle measured. You look at portions of the distribution, all of the distribution. So that's some of the benefits that dynamic imaging has. We can go into a lot more detail about dynamic imaging, but let's go into a practical application. So, when it comes to drilling fluid, I think everybody realizes that particle size is very important. I think everybody here realizes that particle size is a key measurement for a lot of the drilling fluids, both before when you have clean base mud, or when you have evaluating recycling and looking at the cuttings and whatever's left in your sample. So definitely, the use of particle size has been used for cuttings, emulsions, base mud, and also all the different loss prevention materials, which those tend to be not round, right? So particulates are important for a lot of different applications. I think everybody realizes that, and uh, they can help, but they can also hurt. So being able to identify what is in your sample, I think, can really help. Um, Again, some can help, some can hurt. So looking at a practical application, um, definitely, once again, I think everybody realizes that particles play a very big role in different formations, and then also identifying what the loss prevention materials are, the quantity of them is also very important, right? So um, also knowing the blend. So what blend of materials are you adding into your mud is also very important to be able to uh, meet the needs of the well. So where we do see a little bit of a limitation is that there's a lack of field-based equipment. Many people that I've been talking to will actually tell me that they're actually having to take the samples back to a lab, so that could be 8 hours away, um, where they actually then have to take the time to run the samples, and that is very costly. The fact that you cannot make a decision right then and there is very costly. In addition to that, a lot of the field-based equipment that is available is a bit low resolution. The higher resolution equipment generally is lab-based only until now. So dynamic image analysis is a very simple tool. Again, you're just taking pictures of these particles as they go by, and it has the ability of getting high resolution at the well site, uh, but it also gives you the ability of doing the decision right then and there. So the value of being able to make a decision right at the well site with an enormous amount of added information, I think, is of great value. And we're going to talk about the added information in a minute. So um, what we did for this application, we did some direct measurements of some oil-based muds, with and without some prevention material, right? So uh, what we basically did is took some oil-based muds. We got it from an onshore well here in Texas. Uh, Not a whole lot of LPM was added to it. We divided it up and mixed it accordingly to try to see if we could see differences in the different particle size equipment, laser diffraction, and dynamic imaging. And then we definitely then we use isopropyl alcohol 99% to make sure we suspended it properly, right? So again, took the sample, mixed it well to dilute it a bit, went ahead and took about 5 mLs and introduced it into a recirculating system. So most of these particle size analyzers, all of them have recirculating systems to make sure that their representative sampling is done. Not all, but most have recirculating systems. So when we look at the results and we look at the results of a laser diffraction system, you can see that there are some differences. So we took the base fluid, and then we took additional, quantities of adding the loss prevention materials. And definitely you could see that there's similarities. So when you look at the increases over time, looking at the base mud and then working with these added materials, you see that you start getting a little bit of a shift over. Again, when you're working with laser diffraction and you're looking at size only techniques, you're kind of reading the tea leaves, right? You're trying to see what's going on based on a histogram and based on some data. Um, we then took that and actually ran it on an imaging dynamic image analyzer, and we were able to get number-based results. So number-based results, again, will give you for every particle, not necessarily volume calculated. So the number weighted results will give you particle by particle, the number weighted percent. And then what a volume weighted distribution does, it'll calculate the volume over and then give you a volume weighted distribution. And I'm going to show that next. When you look at the number weighted results, very big difference. So if you notice for a volume weighted, you really don't see anything here other than this very small peak, which you would probably tend to ignore. And it's here for all the samples, right? So it's always, even though we're adding some LPM here and we're seeing differences here because they're large, not a whole lot of activity down here. But when you start looking at what's down here, there's a significant amount of samples down here. In fact, in this base mud, when you look at particles from 1 to close to 7 microns, which is just this peak, that represented almost 70% of all the particles in the mud. So you would not see that in a size only or a volume only distribution. This is where you start seeing differences in viscosity, the different rheological properties. You might be running a sample, a base mud, and they are both behaving completely different. You can't really tell the difference, and it could be because you have this large amount of small particles that you're just not seeing. Okay. So here's another example where we actually did a little bit of a difference. We actually added different types of LPMs, right? So we took a base mud and we added same quantities of different LPMs to see if we can actually differentiate by shape, right? So when we look at the difference, if you look at the volume weighted distribution and the number weighted distribution, you can see some information, and you can kind of again read through the tea leaves, if you will, and see that there are some similarities. For example, cedar is very similar to the base fluid right here. If you look at those two peaks, the solid blue and the blue dotted line, um, and you see some differences and some differences, some similarities, definitely available. But again, you really need to look at both. The going away message here is it's important to look at a volume weighted distribution, but also a number weighted distribution. It really is important to look at them both to differentiate by shape as well. So not only size, but there's also shape parameters. Um, what did the sample look like? Something similar to this, again, suspended in 99% alcohol. This is just one image of the thousands that were taken. And again, water droplets would appear as little white balls like this one, and they will impact indirect measurements. So an indirect measurement technique will assume those particles are around. If that was an air bubble, it will be a lot darker. If it was smaller and clear, it would be an emulsion. And definitely, you could see that there's definitely a difference. So let's talk about size only right now. So one of the questions I always get is, will there be a difference in size? And there definitely will be a difference in size. If you're running a dynamic image analyzer and a laser diffraction instrument, you will see size differences, and I'm going to explain why. So on laser diffraction instruments, again, remember, they assume all particles are round. Okay. Dynamic image analysis has the ability of also reporting a size model, again, assuming it's round. So you'll see a laser diffraction distribution up here, and you'll see a dynamic image analysis measurement down here. But what ends up happening is laser diffraction will report slightly larger sizes if the particles are irregular. So if you were just looking at emulsions, I would tend to say that you're going to get some very similar results, volume weighted, to laser diffraction and with compared to dynamic imaging if the particles are all round. If they're not round, laser diffraction will tend to oversize a bit. Statistical differences for the number weighted. So image analysis, dynamic image analysis gives you the ability of getting this same sample and viewing this large amount of small particles. Again, you can measure under a minute, measure tens of thousands of particles, and you'll be able to get a statistical representation of all these small particles. So it will be able to see that significant presence of small particles that laser diffraction cannot. And I'll show it on a video on the following slide, I think 2 slides down. And The reason laser diffraction won't show this information here, so this information, which is in the number weighted distribution of dynamic imaging, that's from 1 to 6 microns. If you look at the graph on the upper right, uh, you don't see that. Very little. You see maybe something right here, a small little bump, and that's about it. The reason that happens is because volume weighted. So when you look at a volume weighted distribution, it benefits more or skews a bit more the large particles. A large particle, a basketball, if you will scatter more forward light than the weaker backscatter light of smaller particles. So the smaller particles that are in there will be drowned out. The light scatter of the smaller particles will be drowned out by the intensity, the forward intensity of the larger particles. So neither technique is wrong. They're both right. They're just different, and it's just important to understand why there is a difference. Okay, to give you a visual representation, here's a sample that's with a number weighted distribution. You'll see here's a number weighted distribution, and then a volume weighted distribution. So this happens to be some frac sands, bauxite for fracking. It's not frac sand; it's bauxite used for fracking. Definitely, you see that there's some large particles, something in the 560, 600 micron range. Those are those big particles. When you look at a volume weighted distribution, you see that there's nothing being represented down here. You don't see a single thing, which leads you to believe that it's a very monomodal sample. There's a lot of, just this one peak. But when you go back to, let's go back to the beginning of the video. When you look at a number weighted, if you look at the histogram up in the upper right, you'll see that's a number weighted distribution. You do see those, let's go back. You do see those particles are definitely there. So again, a number-based technique such as dynamic imaging will give you the ability of viewing the statistics for both of those populations. A volume-based technique such as laser diffraction, unfortunately, will only be able to give you the data of the larger particles because the forward scatter drowns out the weak scatter, backscatter, or higher angle scatter of the smaller particles. Again, neither technique is wrong. It's just important to understand why there is a difference. So going over a few other benefits of dynamic imaging, besides the fact that you get a number weighted distribution versus a volume weighted distribution, is that you get a few other things, such as objective evidence. So this is where it really enables the drilling engineer to make a much more educated decision at the well site immediately in real time. So by having an analysis done and completed and being able to look at the thumbnail images really gives the drilling engineer an idea of what's going on in the sample. No more reading histograms and the tea leaves, if you will, to try to determine what's going on in the drilling fluid. You can actually do an analysis right then and there and see what the images are. Okay. Now, I'm not a fan of saying that dynamic imaging is just a pretty picture taker. It's not. So, dynamic image analysis has an enormous amount of tools that help the drilling engineer. One of the tools, just as an example, we're just going to go over one or two here, are correlation plots. So, the drilling engineer has the ability of looking at these correlation plots that have different areas of distributions um, by doing a correlation of any two shape measures. So in this case, we're doing a circularity versus size. And if the drilling engineer feels that there's an area of interest, you can actually say, okay, what is going on here? This is kind of like finding the needle in the haystack. You can actually zoom into an area of the distribution of particles and say, what are those particles? Show me what they are. And you can actually go in and see what they are by as objective evidence, right? Uh, Another very useful tool is what's called particle classification. Particle classification has the ability, with just a click of a button, to be able to go in and tell you what percent of each sample there is within a drilling fluid. For example, let's say you had a uh, drilling mud, you had some cuttings, and you had some emulsions, and they're both the same size. We can quantify them by shape. And with one click of a button, you can actually go in and say, okay, well, I had 65% cuttings and 27% emulsions. Not only can you do that and quantify the percentage of each one, but one of the nice things again is objective evidence. So show me what they are. Prove to me that they are cuttings, and you have the objective evidence right there. So again, not only are you able to use this outline at the well, an analysis right then and there, but give you an overwhelming amount of information on your sample, uh, and objective evidence with images to be able to make a decision right then and there without having to guess, right? So, in conclusion, again, dynamic image analysis is really a very good tool for monitoring samples, not only by size, but also by shape. And you get the number weighted distribution and the volume weighted distribution. The benefit of measuring so many shape measures is that it will allow you to differentiate the different populations of sample based on shape, and it will give you concentration of each. What's the concentration of one versus the other in a sample? Cuttings um, versus emulsions, right? Or how much LCM do I have versus cuttings? So again, the number-based technique is something that is definitely a complement to the current volume-based only techniques or size-only techniques. And because the technique is relatively simple, you get really good lab quality results. The same quality results you're going to get in a lab, you're going to get in the field because it's the same technique, same measurement, and it's very sturdy. Very ruggedized. Something that is definitely designed for at-line use. With remote operation, battery backed up. Definitely the ability to do these decisions at the well. Overall, in final conclusion, this is still a technique that's still evolving. We're always looking to look at different applications and different opportunities. So as they exist and they come up, we're definitely going to be documenting them more. If there's anybody that has an application that you feel is important and can be benefited by dynamic imaging, let us know. We're always looking for applications. And I would like to thank a few people. I would definitely like to thank Harry Deering and Eric from Genesis Fluids. They were the ones that actually provided the samples for our testing, and definitely would like to thank Brian and Tyrone from OFI, and obviously Sanjeet, which co-wrote this, for helping us out. I appreciate that. And if there are any questions, please contact us. These are our emails: peter@particleshape.com or sroy@offite.com. And again, I welcome your questions or recommendations or suggestions. Thank you.